In this tutorial we will see a couple of ways of computing consensus between different picking algorithms. So let's say that we have used the XMIP automatic picking algorithm. So this is the results that we have, and we have also used the one of rely on Laplacian of Gaussian. So this one is based on the size of the particles, and while this one is based on this one is based on learning from the user what kind of particles he is interested in. So this is the result of rely on, and we see that in this particular case it has tended to pick to match. So here in the picking consensus we can be very creative. So we can combine any number of pickers, and then two coordinates are pointing to the same particle if they are closer than a certain amount. So by default it is 10% of the particle size, and the particle size is taken from the box size that you have used for the picking. You can increase it to 20% if you want. And here in the consensus you can also be very creative. So let's say that you have two pickers. So you may accept a particle as long as it has been found by any one of them. So it has been found by at least one of them, or you may only accept particles if they have been found by the two of them. So here we would say 2, so that a particle is a particle only if it has been found by the two of them. If you have more pickers, like 3-4 different pickers, then you can put your threshold of consensus to any level that you wish. This is one way, and this is relatively simple. The other way of computing consensus in Scipion is by using the deep consensus. So the deep consensus uses the same idea, so that you use different pickers. In this case I have used 4 of them, so I have used Rely on auto picking, Craiolo, XMIP and Topaz, and then each one of these pickers we see that they have a very large they have large differences in the number of particles that they have picked. And the deep consensus will train a neural network trying to identify those similarities between the different pickings. So what is the commonality between all these pickers? And this at the end produces something like this. So we can see, for instance, for every particle we assign a score, and we see that this score is very much polarized. So 1 means that the neural network thinks that is a particle, while 0 that it thinks it is not a particle. So we see that most of them are particles, as expected from decently trained pickings, and then we can try to choose those particles. And so this is the result of the deep consensus. So we can see here, for instance, we can see how the score increases. So this is the same information we had in the histogram, but now plotted differently. So these are not good particles, these are good particles, and then there is a transition between them. So the threshold, in principle 0.5, has some theoretical meaning, but still you would like to see which is the threshold that you would like. So let's go to, for instance, this is 11,000, so let's take the 12,000 particle. They are still very bad. Then we can go to here, for instance, this is around 25,000, 24,000. So So let's go to 24,000, and yeah, they don't look so good either. So now we can see a bit the particle, but we can also see that there are some contaminations here, so we may go further. So let's say 28,000, and now we see particles. So this is apoferritin. So now we see the apoferritin in the images. So it is up to you which threshold to choose, and if we go to the end of the list, they must be the very best particles. So these are very much contrasted, and so at this point you would have to choose the particles to a particular point and deselect the rest and create a new set of coordinates. And with this new set of coordinates you go on your analysis. So this is what we did here. From the 140,000 different coordinates that all these pickers were suggesting, we chose something like 112. So we have rejected these 28,000 particles.